Hello, my name is David Lynch and I'm a consultant neurologist at the National Hospital for Neurology at Queen Square in London. And today I was going to talk to you about the new inherited white matter disorder service, what it does and how we work. And then I also wanted to talk to you a bit about genetic testing. So a very frequent question that comes up is, why does it take so long to get a genetic result once we've had a blood test taken? Genetic tests are very different to the tests done for a blood count or a kidney or liver test, and they're performed in a very different way. And I thought it would be useful to just show you some of the parts of genetic testing and analysis and give a sense of why it takes so long and why it's so difficult. So what is the new inherited white matter disorder service? Well, it's essentially a team. So it's a team that consists of lots of different specialists with different backgrounds and areas of expertise. So we know that IWMDs are really difficult to diagnose because they can often look quite similar in terms of the symptoms they produce, but also what the MRI scan might look like. So we need to draw on expertise from people with experience in genetics, in radiology, in metabolic medicine, inflammation, specialist nurses. And what we do is we come together in a meeting and we discuss patients and their tests and their scans to see if we can suggest ways that we can advance the diagnosis. The aim ultimately is to shorten what we sometimes call the diagnostic odyssey. And that's really the long and arduous journey that many of you will be familiar with when you develop symptoms caused by a rare disease. This diagram shows the twists and turns of the diagnostic odyssey, and what we try and do is make it as short as we can, because we know that when it takes a long time to make a diagnosis, it makes a lot of things more difficult. So what we do at the IWMD service is we put together all the information we can get on the patient and their condition. We think about the possible causes. We think about any tests that haven't been done yet that might be helpful. If the patient has come with a diagnosis already, we have to decide whether we think it's correct. We might suggest treatments or trials, and we might need to see someone face-to-face if something isn't clear. And one question that pops up is, why don't we take over the care of everyone completely? So in the model of care from the IWMD service, really the purpose of the MDT, the multidisciplinary team, is to support local teams. It's not to take over the care of everyone and have everyone be seen centrally in London. And the reason is that we know that local teams have a lot of expertise in managing common neurological conditions whose symptoms are often similar to those of patients with IWMDs. So for example, the symptoms of multiple sclerosis can sometimes be quite similar to adult symptoms in an IWMD. And an MS team locally might have a lot of experience in managing those symptoms, but what they might need is just some guidance or some advice, especially when the patient has a rare disease. We know that local teams often have connections to the best local physiotherapists and occupational therapists that the national teams don't know. And we know that funding in the NHS is mainly driven locally, and we have to work within that even when that's frustrating. So really the intention of the MDT is to support local teams to make diagnoses and to deliver care. Well, what particular IWMDs is the service aimed at? Really the aim of the service when it was set up was to diagnose what are the newly recognised and the very rare IWMDs. There's a lot of different conditions that come under that umbrella. Some are more common than others, and some of the commoner ones are some of the more well described or conditions which we have a lot more experience. They already have services set up. So for example, mitochondrial diseases, or what we would call lysosomal storage diseases, they often have a service set up already to look after them. So sometimes what we do is to just there to signpost that patient to that service. So that brings me to the next part, is genetic analysis, which is something I do a lot of. It's one of my main subspecialties. And so I thought I would talk you through what it is and how it works, why it takes so long, and why sometimes we just can't find the specific mutation causing the disease in that person. So we all have about 20 or maybe 22,000 different genes in our genome, which consists of all of our DNA. And usually mutations, which you can think of as like a spelling mistake in the gene, they occur within genes themselves rather than between genes, as the genes are generally the most important bits of the DNA. A gene will be made up of thousands and thousands of different letters, sometimes 10,000, sometimes 100,000 letters, so they can be very big to actually analyze and look at. But the really complicated thing is, how do we know when we see a mutation or just a spelling change or a spelling mistake, how do we know whether that is in fact causing the disease or whether that's just what makes you you? So these variants, these mutations are also what cause your hair color to be particular, your height, your eye color, your weight, your ability to run. All of these factors that make us ourselves are all encoded in our DNA. So here's just an example of a tiny, tiny fraction of a gene. And we can see it's made up of letters of A's, C's, T's, and G's. And we can just see a couple of areas where there's been a change to a C, and that's underlined. And that might cause a mutation. That might cause a change in how that gene works, or it might not. And so the difficult thing is working out whether that's an important change or not. We know that although there are a lot of similarities between the IWMDs, they are all obviously individually different. And that's because they can be caused by different genes, and those different genes might work in different pathways, and those pathways may cause different mechanisms for cells to not function properly, and that might produce different symptoms at the end of the day. We have a lot of complications, particularly in adult person with a leukodystrophy or an IWMD, because the easiest way to do genetic analysis is to compare the DNA of someone who's affected to the DNA of a family member who isn't affected and look for the differences that are there. But when we're talking about adults, often we don't have DNA available from that person's parents or siblings. Usually that is available in a child, so that can sometimes make it easier in a child. But for adults, our hands can be tied in that way, and that can make it harder to do the analysis. Harder because you're not looking for any differences there. And what if the condition, especially in an adult, isn't even genetic? What if it's just a mimic of a genetic condition? And then we could spend a long time looking at the DNA and not find anything, because ultimately that's not where the answer lies. And we know that vascular disease, so diseases of the blood vessels like hardening of the arteries as we get older, everybody gets this. But if it's particularly more advanced in some people, then it can give a similar imaging appearance. So the scan can look the same as an IWMD. So that can really confuse us. Another big complication when it comes to genetic analysis is that we can have too much or too little information. So in recent years, and say 10, 15 years ago, what we were mainly looking at were what we called exomes. And this is just the bits of the DNA from the genes that we consider to be the most important. And we know that about 90% of all mutations lie in those important regions. But interestingly, those regions only make up about 1% of the total DNA. So the rest of the 99% makes up the genome. And what in the past, you may have heard the term junk DNA. And that's the bits of DNA that are between all the genes or within the genes. And that actually makes up the vast, vast, vast majority of the genome. And we, in the past, couldn't actually sequence that. It was just too big. There was too much information. But recently, we have developed tools to analyze the whole genome. And this gives us a lot of information. But to be honest, it gives us more information than we can even analyze now. It's just too much. To further complicate matters, sometimes mutations aren't even spelling mistakes at all. So if you're scanning a document or a page of a book, often a spelling mistake might jump out at you just very easily. But sometimes mutations aren't spelling mistakes, but what they are is just an area where information is deleted, or it's doubled, or it's rearranged or flipped in some way. So if you're looking at a paragraph of text and there's just a sentence missing, well, it might be obvious to you because maybe when you're reading it, you'll see that things don't quite go together properly. But many paragraphs would read perfectly normally if we deleted just one sentence. And so that can make these types of mutations really hard to detect. And in the past, we just couldn't detect it at all, but now we can. We're learning how to, but this is very much still in its early days. So what actually happens when we do a genetic test? Well, as you might know, you'll go and have blood taken. And then the odyssey to analyze the DNA begins. But first, we have to actually take the DNA out of the blood. So we have to extract it. And this is different to how when you go to the hospital for a blood count or a kidney test or a liver test. Those tests are just performed on the blood itself. So they just put the blood in a machine and it looks at the kidney function and spits out an answer. But actually to extract DNA from blood is a multi-step process and it takes a few weeks to do it properly. But the good thing is that once you have done that, then you can keep that DNA forever. We usually keep it frozen and we could do tests on it in 40 years, 50 years, even 100 years if it was good DNA. Then the DNA gets sent to a centralized lab to be sequenced itself. So actually to put it in the machine and get all those letters out that can constitute the genes. And we know that all of the DNA sequencing now is done by Illumina, which is a big genetics company, and that's all done centrally. And then they send the data back to the referring lab that you might have gone to the hospital to have the blood taken in. And if this is a genome, it will be an enormous amount of data. It will be hundreds of gigabytes of data. So, you might struggle to keep more than one or two individual genomes on a large laptop because of the amount of space they would take. And it's literally billions of letters, so probably about 3 billion letters comes back from that lab. And then the really hard bit begins, which is actually the analysis. So what happens now is that a scientist working in the lab will start to look at the enormous amount of information, and then they try to sort out what's what. I've shown you here just a screenshot of a person's DNA sequence that I've been looking at. And we can see down here in very tiny writing, there's 182,000 lines in this Excel document. So, 180, nearly 200,000 variants to look at and try and decide which one of them, and it will only be one, is causing the disease. And so what we do is, we try to get rid of the variants that we think are not relevant. So things that are maybe common in the population. So if a variant is in 5% of the population, that we know it definitely can't be causing a very rare disease. Even if it's in 1% of the population, it couldn't cause a rare disease. So first thing we do is we get rid of anything that's common. Then we try to see if anything looks like it would cause a really bad spelling mistake in the gene. And we have sort of tools, software tools that can help us with that. We might look and see if any of those changes are in genes that we know cause an IWMD. And if they do, does this spelling mistake even matter? So sometimes spelling mistakes, they don't matter at all. If we think of spelling differences between US and English and British English, if I spell color with a U or without, you can still understand it. So when you're reading it, I can still get across the same information. But, some spelling mistakes really do make a difference to what the word means. And so that's really important for our analysis. Scientists, they do have guidelines that we'll use to see what variants might be important. But the thing is that in genetics, we can't just think something might be important. We have to really prove it, and we have to be certain, because big decisions get made on the basis of these tests. This can really influence people's lives in a big way. So we have to have a degree of certainty that we don't have in other areas of medicine. And that makes this very time consuming because you need to be really sure. At the very end, we need to decide, does that mutation make sense from what we see in that patient and their scan and all their other tests? So the lab scientist will discuss with the treating doctors and our MDT, does this mutation make sense? And if it disagrees, if we don't think this is likely, they have to go back to square one and start the whole thing all over again. So you can easily see how, if we go from step one, you have your blood taken, the DNA is extracted, that takes weeks. Then it gets sent somewhere else to be sequenced, that takes weeks. It then comes back, and then we start this enormous analysis, which takes months. And then at the end, we have a lot of discussion to see whether we think this is correct and if we're certain about it. And if we don't, then we start the whole thing all over again. But if it goes quickly, we might have an answer in 6 months, maybe 4 months. There are times sometimes when the analysis might be done extremely quickly, like if a patient is very unwell and maybe in the ITU, and we think that the genetic answer might change treatment, then things can be done on an emergency basis, and that might take 2 weeks. But in general, an analysis is going to take months. So why do we do this? I mean, it sounds overwhelming and frustrating. Well, we do it because if you don't know the gene, you just can't start anywhere with the disease. You just don't know what processes are going wrong and in what cells, and you've no way of knowing how to even start treating the condition you're dealing with. And we do have success. So although this sounds very difficult and frustrating, we often are able to make genetic diagnoses, and genome sequencing is amazing. I mean, it's really cutting edge, and the NHS is the only health system in the world that offers genome sequencing at no cost. And that's an area I think that we are really leading the world in. Gene therapies are coming for lots and lots of diseases, and we have had success in having some be approved and show that they work. So this is something that we do need to continue doing, and hopefully with advances we can develop more treatments for IWMDs. So to sum up, this is just really hard and it takes a really long time. There's always things we can do better. So I think although it takes a long time to do genetic testing, we shouldn't really just accept that that is necessary. We should try to make things faster. The whole point of the service is to speed up diagnosis. So we should always be trying to improve our timings. We should always be communicating with the patients and the families. We need patients and families to understand what we're doing, why we're doing it, why it takes so long. And we have to be able to live with uncertainty, because sometimes we just don't get an answer. We should always keep pushing forward and not giving up. So genome sequencing is amazing, but there's further newer technologies that are coming, and we should be trying to incorporate those into what we do as well. Of course, taking part in research is really how we push the field forward and how we try to make new diagnoses. So I hope that gives you a bit of an overview of what we do at the service, how we do genetic testing. And it's been a pleasure to speak to you today. Thank you.